this presentation, I would like to talk about missing data. Missing data winds up being an important issue to consider in longitudinal research because when you follow people over time, almost inevitably you wind up dealing with issues like attrition or just simply people being present in one wave but not in another. And so missing data is something that we frequently have to do something about when we go to do our data analysis. And today I'd like to talk to you about some different options when it comes to handling missing data, and also why we might want to choose some options over others. There are different kinds of missing data, and these are terms that you may or may not be familiar with, but they are generally thought to come in three different categories. One type of missingness is called missing completely at random, or MCAR data. And in many ways, this is the ideal scenario for missingness because it's completely unsystematic. In other words, if you just had all of the cells of a data set and you randomly made certain cells missing, that is in essence what is the case when you have MCAR data. There's no pattern, no discernible pattern for why the data are missing. Another type is called missing at random, or simply MAR data. And in this situation, there is some sort of systematic trend to why the data are missing, but we have some sort of predictor that accounts for why certain data are missing. So for example, if you have a situation where men are more likely to disclose information in some other variable, you have a predictor, in this case men, and by knowing that somebody is a man or not, you have a predictor for why another cell might be missing. And then there's missing not at random. And this is definitely the worst form of missing data. This is when the value on the variable of interest is actually why people are missing on that variable. So think about a situation where people with lower levels of math knowledge don't complete a math assessment. So when you looked at those people, all you would see is that there's missingness, but the missingness is in fact on that given variable. And so that is relatively problematic. Now, we have some tools for trying to figure out what kind of missingness we have, but these tools are far from perfect. One tool is called Little's test, and it's a pretty conservative test, meaning it's easy to violate it, where it's a test saying, are these data MCAR? And it's relatively easy to get the answer back no, but if you can show that your data are missing completely at random using Little's test, that is a nice thing to be able to say. Now, with respect to missing at random data, what you can do is dummy code each variable for whether or not you have missingness in that variable. And then you do t-tests on other variables to see if having data on that variable or not is related to other variables in the data set. And if they are, then you know that you have a predictor of missingness and your data are MAR. The problem with data that are missing not at random is that we don't even really have a test for it. So when you don't have a predictor for the data, the missing data, it suggests that there may be some other predictor that's not in your data set, or that your data are just missing not at random. The missingness is due to the variable that you're missing on. And what sometimes people do is they follow up with people in a different way, the people that didn't complete an assessment, and they try to figure out why that might be. But you have very few options if you're dealing with a secondary data set when it comes to doing anything, or even to some extent figuring out if your data are missing not at random. Oftentimes we approach a given analysis with the belief that we have missing at random data, and we're going to just find predictors and model those. Now, when it comes to doing something about the missing data, the default in most software packages is listwise deletion. And because it's the default, it's super easy. So many people are doing listwise deletion without even really thinking about the fact that they're doing listwise deletion. And it might not be until they see like a degree of freedom output thing where they start to think about, oh, I've dropped a bunch of cases. Now, listwise deletion deletes a case from an analysis if it's missing values for any of the variables in the model. So what variables you are including in the model winds up being an important thing to think about. If you've got one variable that is missing more values than another, all other things being equal, you would include the one that's missing less data. Hopefully that makes sense. So missingness and listwise deletion are often go hand in hand, and it's important to stop and think about what's happening with listwise deletion. Now, first and foremost, you're going to lose some power. Because you're dropping cases, you are losing degrees of freedom, and therefore you're losing power. So that is something that's just there, and that's may or may not be an important consideration, but it's often something that you want to keep in mind. I would say by far the most important consideration isn't power. It's the fact that you have lost the ability to generalize to your entire sample. And I'd like to say just a little bit more about that. We often go through great pains to recruit a sample that we think will be meaningful for our given study. And even if we haven't been the ones to collect the data, we often go into quite a bit of detail in our participants section about who this sample is. And yet, when it comes to our data analysis, we could be dropping 10, 20% of our sample. And all of a sudden, the people that we are doing the analysis on are not the same people that we described in our participants section. We've dropped all those cases, and so we've lost the ability to generalize to that sample, that larger sample. We can only generalize to the people that we've included in our analysis. And that is something that we often want to avoid. And so listwise deletion means that we need to reconsider who it is that we're describing is our sample, because we are no longer generalizing to the total population that total sample that we had originally collected. One alternate approach that is low-hanging fruit, because it's also quite easy to do, is to do what's called mean imputation, mean the average here across the values for a given variable. And if you think about it, this makes quite a bit of sense. The mean, if you had to make a single guess for what a given person's value would be, a mean is the best guess for that person's value. And so it just extrapolates that thinking, and it says, well, for any given missing value, you substitute in the mean. And that does make a certain kind of sense. However, this has an unintended consequence that is easy to see once you think about it. If you think about the normal curve on the left as representing the variance for a variable and the peak being the mean. So if you pile a bunch of scores up at the mean, what happens is that you get less variance. The variance is reduced because you've added several cases that are at the mean. And in statistics, variance is the name of the game. It's all about variance and covariance. And so tinkering with the variance like that, although we're recreating the mean, which makes a certain amount of sense, we have not recreated the variance of the variable. In other words, the mean before and after the imputation is the same, but the variance before and after is different. And whenever we do a imputation procedure, we want the mean and the variance to be the same before and after the procedure. So a point here that is really worth dwelling on is that we want both. We want the mean and we want the variance when we do an imputation. This brings us to a different technique. It's a little bit more sophisticated than mean imputation, and it's a regression-based imputation. And here we're doing a better job because a mean, that's almost too easy. And we might, in fact, know that the mean does not best represent a given case. So if we know something about a case, we might want to predict it. And so let's say we're imputing math scores and we have reading scores. Well, we know that there's an association between those two things, so we can adjust it. Or if boys score lower than girls, and so that's what that's getting at with that normal curve here, is that it's showing you might actually slide scores down if it's a boy, or slide them up if it's a girl, or take into account the association between these two, something that you have and something that is missing, and it adjusts the score based on that. So this is good. It's more sophisticated. It's going to be more accurate. But although it's more accurate, it's going to still cause some problems with that variance. It's going to be better because it's going to represent the data better, but it's still likely to pull values in and in general just not recreate that variance. So better, yes, than mean imputation, but it still hasn't gotten us out of this box of recreating both the mean and the variance. One procedure that, well, many people haven't heard of is called hot deck sampling or cold deck sampling. Sometimes people call it hot deck imputation, same idea. And what you do with hot deck sampling is that if you think about a column of values and some of those values are missing, what hot deck sampling does is it looks in that data set and it says, okay, I'm going to randomly select a value from somebody who does have data. And so it takes somebody else's real value and it inserts it into a missing cell. Cold deck sampling is the same idea, but instead of using the current data set, you would have some other data set with the same variable that it would select from instead. Now, in some ways, this is really helpful because if you think about, let's just think about a case where there's a normal distribution of values. Well, what that means is that values closer to the mean are going to be more prevalent in the data. And so just by chance, by randomly selecting values, it is likely to choose more values that are closer to the mean. But because it's a probabilistic sort of thing, every once in a while it will grab more extreme values. And so in that way, it does kind of reproduce the mean, and it does kind of reproduce the variance. So it has some ability to recapture that, and they're all going to be plausible values because they're all already present in the data set. And this does seem to be fine for small amounts of missing data. But there have been some simulation studies that have shown that the covariance is inflated and the variance is reduced. So some of those same problems that we were hoping to get away from are still present in the data. And if you just by chance, it might grab an extreme value, or it might grab a non-extreme value for somebody that really would have scored more way out. And so it just isn't doing an awesome job recreating what was originally there. And so it's helpful and it's easy to implement. And there are definitely times when you could do this. But I would really only do this if you had a small amount of missing data. For me, when I say small, I'm saying like 2% or something pretty small. And now we're starting to get to a much more sophisticated and ultimately helpful idea. And that is called stochastic regression. Now, stochastic regression, stochastic means like random, and there's a element of randomness built into this regression. So we've already talked about regression, where you can have a model that has some predictors, and a stochastic regression can have that. But it's going to also interject an element of randomness. Now here, randomness isn't like totally random. It's more like it's going to adjust a score not only based on the predictors, but based on some element of the variance as well. So it's going to take a score and say, okay, it's somebody who scored higher on their reading, so we're gonna adjust this guess up a little bit. But then it's going to look at the distribution around that missing value, and it's going to say, well, it might be adjusted up a lot very infrequently, or it might be adjusted up quite frequently. So like think about that normal distribution and think about the ability for it to just make bigger adjustments less frequently and smaller adjustments quite frequently, because a lot of values are closer to the middle. And so it just kind of randomly selects an amount that it's going to make that adjustment from, but it's based on the probability of it being extreme or not. So it might make an extreme adjustment very infrequently. So it's probability based. And what that means is that two different stochastic regressions will not give the same value for a missing variable, because sometimes it will have Like most of the time, it's going to have a small adjustment up or down based on the variance of the variable. But every once in a while, it will give a bigger deviation from that score based on a somewhat unlikely occurrence of it being out at the tail end. Now, that idea by itself is kind of weird, but where it gets its power is if we do it multiple times. So when we say multiple imputation, we're frequently referring to multiple stochastic regressions. So multiple imputation here is this idea that we're going to run that same procedure multiple times. And each time the answer is going to be a little bit different. Most of the time it's going to give us a cell value that is close to the adjusted mean, but it's going to let it vary, and it's going to let it vary proportionally to the variance of that variable. And so over time though, think about a data set and you impute the missingness, and then you averaged those data sets together. What in theory should happen is that not only would you get the mean of the variable from before the imputations, but you would also get the variance of the variable. And that then is super powerful, because over these data sets, it's not about any one data set. It's about the fact that over these data sets, we have created the mean and we have recreated the variance. And that means that when we do analyses, not with one of these data sets, but when we run the analyses with all of these data sets, we can then average our results and get results that would represent the associations that were there in the original data set. But we have done so with all of the power. We've done so with all of the cases. We've only imputed the cells that we're missing. And usually we don't have to impute like all of the values for a person. So we've taken what we know about a person and we have done the analysis with what we know, and we've imputed the rest, but the imputation has taken into account all of the information across people that we know, the associations that were there across people. So this is what multiple imputation is. It's using a procedure that recaptures the mean and the variance, and then we make multiple data sets, and in so doing, it mitigates the effect of a quote-unquote bad guess. In other words, it might have somebody have an adjustment in some cell that is too big or too small, but on average, it's still going to recreate the best guess, which in some ways is the mean. So with that as a backdrop, you may wonder, when should you do multiple imputation? Well, I don't mean this to be a pithy answer, but anytime you don't want to do listwise deletion, you should be doing something relatively sophisticated. So anytime really, or anytime that you're not doing something in structural equation modeling. So structural equation modeling has a different missing data approach. Its estimation procedure is called full information maximum likelihood. Usually people just abbreviate it and then call it FIML. So SEM uses FIML for its estimation, and that estimation also accounts for missing data. So you don't have to do multiple imputation when you're doing SEM. And I would say if you've got 5% missing data, that's then coming to be a pretty substantial amount of your data. And you should probably consider doing multiple imputation. And as you will see, it is, although it is a little intimidating, it's actually not hard to do. It's not hard to make the multiply imputed data sets, and it's not hard to analyze with them either. And you put those two things together and it's like the bar should be pretty low for doing multiple imputation. So that's where I come down. Now let's circle back to this idea of the different kinds of missing data. So we said there's MCAR data that's missing completely at random, MAR, which is missing at random, and MNAR, missing not at random. So each one of those has different reasons why the data are missing. So how does the reason why the data is missing, how does that inform our thinking about multiple imputation? Well, let's start with the easiest one, which is MCAR. So you did Little's test and it says your data is MCAR, which is pretty good news. And that doesn't mean that you shouldn't do an imputation procedure. It's just that your reason for doing so is essentially just to get you additional power. You don't have to throw out the cases that have any missingness. So you get to use all of the people that you have data on, and so you get to fill those values in, and in doing multiple imputation, you haven't introduced any bias. So you can do the multiple imputation and you would theoretically get the exact same B's or betas regardless of whether you did multiple imputation. It's just a matter of the power being different. In other words, your p-value should theoretically be lower for the multiple imputed data, and so you've got more power but the same beta. Then there's MAR. So remember, MAR data, you've got a predictor of the missingness. So what that means is that when you do the multiple imputation procedure, when you do the actual stochastic regression, you include those predictors as predictors of your missingness. So you include those as predictors in your model. And in so doing, it can make those adjustments to its estimates for the different people. And because you've included them, you can then have a data set that isn't as biased as if you had done listwise deletion. If you had done listwise deletion and you have predictors of missingness, then you can introduce bias into your results. This is a way to actually get better results, less bias in your estimates. And we get more power. So this is good and good. Now with MNAR data, remember this is when you don't have any predictors of missingness. And if you were to do multiple imputation, it would get you additional power because it's giving you degrees of freedom to use, so of course. But the problem is it may actually introduce bias into your results. And in other words, think about it. If you have a bunch of people that are missing their math test because they view themselves as not being good at math, what that can do is when you do the imputation, the procedure doesn't know that. And so it's not likely to give them values that reflect their ability. So it's going to be misestimating their values. and it's going to do so systematically, and therefore it is going to introduce bias. So this is a really bad situation, because if you don't do the imputation, your results are going to be biased because you've left out the people that, or you're more likely to leave out the people that had the lower scores. But you're also introducing bias, a different bias, if you do the imputation procedure. So if you're getting the sense that MNAR data is bad, you're getting the right sense. MNAR data is bad, so we really want to avoid it. So please note, multiple imputation does not help with MNAR data. Now, a common question that people encounter is, well, how many data sets should I make? Because it's arbitrary. You could make 2, you could make 200. So how many should you do? I'm going to say just make 10. 10's good. Fewer really doesn't make your life any easier. So, for example, 5. 5 seems like a good number. 4 used to actually be a relatively common standard, but it has gone up as it's gotten easier. And so now 10 is pretty standard. And so I would say just do 10. Doing more than 10 doesn't really buy you much. Like if you think about what a multiple imputation is trying to do, 10 does a good job recapturing the mean and the standard deviation. And if you did an analysis where you did 10 multiple imputations, I have a hard time imagining that some reviewer is going to be like, you only did 10, I want you to do 20. It's just not something that's likely to make that kind of difference. It will make a difference if you don't do multiple imputation and a reviewer says, I would like you to do that. But I think the incremental gain from anything more than 10 to 10 is really pretty small. Now, the one caveat that I would put on this is that the more missingness you have, theoretically, the greater number the data sets that you might want. And theoretically, there's not really an upper bound to multiple imputation's ability to capture or like recreate the mean and standard deviation. And so, you know, if you had 50% missing data, theoretically, all you would need is more data sets to have certainty that you're recreating the mean and the standard deviation. In practice, having 50% missing data just isn't really going to fly no matter how much imputation you do. But I'm trying to give you some practical bounds here. So 10 is a decent approach, and you can do more, you can do less, but I think 10 is a good number. Another thing that comes up is in the imputation procedure, it can give you values that were not present in the data set. So let's say you have a variable and it's on a 1 to 7 scale, and some of the values are missing, and then you go and you do the imputation, and you notice that sometimes it's estimating people to have a 9.5, and other times it's even estimating that people have a -1. And you go, well, this is on a 1 to 7 scale. How can that be? Well, just remember, it's adjusting those scores based on a normal distribution and just the chances of an extreme value. And so every once in a while, it might predict a value that is not plausible given the actual data. So you might think, well, I'll just restrict those down. So anytime it gives a value above 7, I'm going to just bring it down to 7. And likewise, anything below 1, I'm going to bring up to 1. And I admit that that makes a certain kind of sense, but multiple imputation is not trying to recreate means and variances across a single data set. It's trying to do so across multiple data sets. And in fact, if you leave those extreme values in there, you will see that the mean and the standard deviation are recreated quite well. And so my advice to you is to not change anything. There's really no reason to. Now, a closely related issue that I will mention here is, well, what about the descriptives? I mean, papers, you have to report descriptives, and so isn't that going to look weird? And this is how you should handle it, and just how we should approach these anyways. You don't report based on the imputed data sets. You report the actual observed values. You go to that raw data set and you report the mean and the standard deviation for every variable and what percent missing there was on that variable. And that's the table that you report. Another topic that comes up is whether or not you should impute outcomes. And it just feels weird. How can you be imputing the outcomes? Isn't that cheating? But the logic for outcomes is exactly the same as the logic for predictors. And I mean, most of the time it is actually arbitrary what is a predictor and what is an outcome. And so I would say the logic is the same. The entire multiple imputation procedure is set up to recreate all of these things. And so, yes, impute the outcomes as well. But of course, be transparent about what you're doing. And so when you're reporting those outcomes in the descriptives table, talk about the missingness in those too. And then lastly, we have this idea of imputing interactions. So it's a little bit weird to think about, but let's say you've got two variables, x1 and x2, and each of them have some missingness in them. Well, one thing that you could do is impute on x1 and impute on x2, and then after the imputation procedure is completed, then you compute your interaction, just like normal, and nobody will be missing on that interaction because you have actually you have made sure that x1 and x2 are complete. So that does make a certain kind of sense, but that is not what you should do. What you should do is have x1 and x2 and their interaction. Now that interaction is going to be missing on any case that is missing either x1 or x2. But you have all of those there in the data set when you go to do your imputations. And this may not make sense, but believe me, if you leave out the interaction when you go and do your imputations, you're actually precluding the fact that there is an interaction when it's figuring out those values. So in other words, if there is an interaction, that interaction should be present in the estimation for the interaction value. And so you have to let it be there in order for the estimate to be correct and allow for it. I know that's a little confusing, but it is true where if you are going to be testing an interaction, you want to impute that interaction. Okay, well that just about does it here. So hopefully that gave you a good backdrop for the different kinds of missing data and the different missing analytic procedures, and ultimately how multiple imputation uses stochastic regression multiple times to recreate data sets that have the same mean and variance for each of the variables that can then be used in analysis.